All right, so let's now look at our example 2. So my entire aim of this example is to give viewers an opportunity to work along and be fluent with the steps of how we can find a general derivative for any given function. Okay, and in the end, in order to be successful at any math course, we need to repetitively practice those kind of concepts being introduced in the course. And so generally, for example 2, we're going to be just finding either f prime of x or finding dy dx, depending on if the function, how the function is written originally. And of course, it's also my intention in this example to not only to give viewers an opportunity to be able to find the derivative generally, but also be able to get comfortable with how we use notation and symbols appropriately. Okay, all right. So basically we want to find derivative for different various functions I'm about to give here. So part A. So how about our function f of x is the simple function 3x plus 1. So this function on its own is a linear function. Okay, but whichever function that is, the point now is that, what's first thing to understand here is that this function currently, the way how it's given, it's written in functional notation, not like a y equals 3x plus 1. It's f of x equals 3x plus 1. And so in that way, I am going to use this symbol to be appropriate. So correspondingly, I'm going to be using f prime of x symbol. And we now finding the f prime. So once again, famous starting setup right here. F of x plus h. It never hurts to repeat this famous starting setup right there. Minus f of x. And we refer to this as the limit definition. H goes to 0. So that's the famous starting setup for finding any general derivative of a function. And this is also known as the limit definition. It's a definition of our derivative, and it heavily relies on the limit concept. All right, so our function now, we're going to substitute we are going to substitute x plus h into our function's inputs, where the input here is x. So we're going to replace x by x plus h, and that's the reason why now see 3 times the input. So now it's 3 times in parentheses x plus h plus 1. And or maybe I should write that in the bottom line here, because currently I don't have enough space. But so 3 times x plus h plus 1. This is our function f of x plus h. And now we are going to subtract 3x plus h, which stands for f of x from our previous starting setup right there, divided by h. And of course, we need to introduce the limits problem once we finish setting up the famous difference quotient. All right, and so getting on to the next step right here, then of course things are quite simple now. 3 times x plus h from the previous board here is, we can now simply distribute in, okay, do a quick little distribution for each one of these steps right here, and allow me to, well, anyone learning calculus up to this point is hopefully fluent enough so that I can start, combining 2 little steps into a bigger step. Okay, and so in my next step here, I'm looking at 3x plus 3h plus 1, and completely remove the parentheses. But now for the next pair of parentheses, since there was a minus sign, so be careful when you remove the parentheses. Okay, so it was minus, but 3x plus 1 inside parentheses, so you are going to, it's gonna have to become, it's gonna have to change signs here. Okay, and so now I'm looking at minus 3x minus 1. Okay, and over h. And that's how I keep working out with my difference quotient in every step And so at this point, we are going to have a massive amount of like terms to collect right here, or as well as opposite terms to cancel. So the 3x cancel with the minus 3x. The 1 cancel with minus 1. Okay, and so now my left behind expression here is going to be just simply a 3h over h. And that gives me h goes to 0. Okay, and so, and we just brought ourselves to that step, and we recognize further without any further factoring or anything like that, but we can cancel out the common factor h here. So now our expression becomes just simply 3 as a constant, and we take limits as h go to 0. And now at this point, we are completely safe to treat the problem with direct limit laws, meaning we're going to work with it out like substituting it. And so final answer is 3. Okay, so just because we have a final answer being a finite numerical value right here, but remind yourself, that means what we have found here is f prime of x. Our starting function was, remind yourself that our starting function was f of x equals 3x plus 1. And so now, looking back at this thing here, we are finding out f prime. So f prime is found to be 3. And so it's a function of x, but there's no x involved in our final function here. So I just need to remind that term. So it turns out that our derivative for 3x plus 1 is a constant. So its derivative is a constant function, 3. Okay. All right. So let's look at part B of the example. So I don't want to give too much explanation. I don't want to make too much explanation about the meaning of each of our answers here in our example 2, because I just want to mainly aim at the particular skill how we can find general derivative. So how about let's find f prime or dy dx, depends on how your starting function is written. So part B, let's be given a different function here. How about g of x equals 5. Our function is a function g of x equals 5. The function name is no longer f. I mean, so here it's just the representative only, but when it's g, then you're going to have to go with g prime. And by the way, your function is written in functional notation, not in the equation format yet. So now, of course, I'm going to write g prime. We're looking for g prime of x. And g prime is set up. Let's go ahead and throw in that starting setup again. We need g of x plus h. And like I said, it's never going to hurt to just keep writing these, this starting step right there. G of x plus h minus g of x. We're dividing that by h. We take limits as h approaches 0. Okay. And now, since our function itself, and notice and observe, how about observe our function before we move on any further. But you have learned that back in algebra, but this kind of function, it could be a 10 there, it could be a negative 1,000 or whatever, but in the end, this function is regarded as a constant function. Make a good note of that. And then later on in the next lecture or in the next couple of lectures, I am going to formally get to that. But here, just simply understanding that it's a constant 5, g of x equals a constant 5. That means regardless of whichever input, it could be x here, it could be x plus h, it could be 3,000 plus h, whatever we're substituting for the input, your function output value remains the same. So we're looking at 5, and I guess I don't need that my fraction bar to be that long, but 5 minus, and that's surprisingly done for g of x plus h. It's 5. And now minus 5, okay, and divide by h, and here we of course have to take limit as h goes to 0. Okay, and so let's continue a little further, see how things turns out. Okay, so 5 minus 5, opposite terms got canceled out, and now we're looking at 0 over h. And now we're attempting to take limit as h go to 0. But look at how good that is. 0 over h. Now 0 here is a number 0 already, so that means before h even becomes 0, before h becomes 0, the whole expression here, the entire expression here is a 0 value. So that means our final answer here is a 0. Okay, so what does that mean for us? Well, we did a lot of limits, so hopefully the viewers didn't lose track of what you were doing, but that means our final, so allow me to write on the other board there. Our final concluded answer here is g prime of x. In our case, g of x equals 5, g prime of x equals 0. Okay, and I've had that demonstration earlier about what it means by having a 0 value for it. It means your tangent line becomes a horizontal tangent line, and we'll talk more about that later on. We'll get more detail about that. All right. And so now we found another problem right there. We've worked through another problem on part B, same example 2. Let's now look at question C, or part C of our example 2. Okay, so question C. Let's say, this time let me challenge everyone. How about we have y equals square root of x. Okay, so we've been dealing with squares, linear function, cubic functions, power functions, right? And not too more formally at this point in your calculus learning. I haven't introduced anything fancy about the powers yet, but we have found some formula. I mean, we have found some general derivatives for a few of them. And now we're dealing with square roots. Okay? Just want to emphasize that the limit definition works just fine on any function. Trust me. For the rest of your calculus learning, eventually you're going to run into trig functions, sine and cosine, tangent functions, e to the x, logarithms, inverse functions, all of those functions. Everything start out with a limit definition. You got to imagine how important that is, how fundamental that limit definition of finding a general derivative is. So now you're looking at a square root function. So the only thing I brought up here, and one other reason, I should have said that, one other reason I brought that problem here within our example 2, because I want anyone to get comfortable with the idea that we can use interchangeably the two symbols here. So the appropriate one, the corresponding one we should be using here is the dy dx for derivative. Because our starting function, yes, it was an x squared function, but in the end the original function was written in the form of an equation. So there we go, we call that dy dx. But the starting famous setup again, let's go with of course this is still f of x. So we're looking at f of x plus h. It never hurts to write it like that, even though we kind of didn't know exactly what f was, but it's this function. Minus f of x minus over h, take the limits as h goes to 0. Okay, and then so now in our expression, well, assumingly that this is f of x, then f of x plus h means we're going to take the expression x plus h and substitute that into our square root function entirely. So that means now square root is going to contain entirely x plus h inside of it. And then we're going to subtract. So this is f of x plus h right here. And now we're going to subtract square root of x, which is f of x, and we're dividing by we're dividing by h. Okay, so now we have a difference of 2 square roots. And again, square roots are nasty, ladies and gentlemen. I mean, trust me, I was once so hating square roots, and many of my students, generations by generation, hate square root. So yes, we hate square root. So what do we do when we hate it so much? We're trying to find a way to get it out of the square root, or clear the square roots out. Just like denominators. We so hate denominators, and we always have to find ways to clear out denominators. So just like that. Now I've been introducing that famous trick since previous lecture with a difference of 2 square roots like this. Allow me to bring that into the next board here. But so with our current problem, with our current step previously, square root of x plus h, which everybody hates so much, we have to try to get a way to clear out the square root over h. So what I would do, I am going to multiply the numerator with its conjugate. Remind yourself, if you don't remember at this point viewing this video, roll back to the earlier videos lecture when I use a lot of that trick about the conjugate right here. But see, the conjugate, the repeat of the 2 terms, and then here's minus, here's the plus. Okay, that's what I call it, a conjugate. So now, but the rule of algebra, again, any expression you multiply in the numerator, make sure that same expression is divided away in the denominator. So that means I'm having something like this, square root of x plus h plus square root of x in the denominator. But now the usefulness of doing, this action right here where you apply the conjugate is that, and don't forget that we are in the end looking at a limits problem, but currently at any of the steps right here, we're not able to take the limit laws directly yet, right? And so now if we multiply the 2 factors in my numerator here, then we're ending up with square root of x plus h, keep the square root the same, but now we're going to square that term, minus square root of x, and all being square. And now in the denominator, x plus h in square root plus square root of x, and in the end it's a limits problem. But this is a huge victory right here, because look at how good that is. Square will cancel with square root. The square here will cancel with that square root particularly. And so in my next expression, look at how good it's going to turn out for us. And there anyone can start saying like a yoo-hoo, it's things like that. But x plus h here will no longer have the square root outside of that. Minus x will also no longer have the square root attached to it. And over h, actually, it was a little rushing. H times the big nasty looking x plus h in square root plus square root of x. We take limits as h goes to 0. And at this point, well, what we can do, cancel out the opposite terms. So in the next step, I'm looking at h all over h, but factor out, and I should have also mentioned, even though you probably all realized, we actually shouldn't, even though we could, but we shouldn't multiply it through because it's making things harder to see. So why don't we, and that's what I did. I just left it the exact same way without distributing in the values there. So here in the next step, h, and then in parentheses, square root of x plus h plus square root of x, and then taking the limits as h, go to 0. Okay, and so now recognizing that h in the numerator and h in the denominator, they are common factors again. Those two, in the end, they are common factors. And so in that way, I am going to cancel h away. My numerator simply becomes 1, not a 0. Okay, sorry, but at a lot of points I have to keep reminding those surprisingly little algebra, but it can become huge mistakes sometimes. Okay, and in the denominator, we're now looking at square root of x plus h plus square root of x. Okay, and take the limits as h goes to 0. Now, believe it or not, because the expression is still looking a little complicated, but this expression is actually safe for us now to directly apply the limit laws. So limit laws now guarantees that, and of course, if you want to throw in a few other steps, that's fine, go for it. But I can see that here we're looking at 1. The numerator is a constant, so it remains 1. It goes to limits 1. in the denominator, eventually it will become x plus 0 plus an inner square root and plus another square root of x. The next term here is completely independent, so we don't even have to bother with having h in that or not. So in the end, ultimately, now let me swing back to my other board right there. But so this worked right here. So all that there, our final derivative is and carrying from the earlier steps. And now we're looking at 1 over 2 square root of x right here. Okay, and this is our final answer, being regarded as the general derivative of this function. But so now, or as the overall conclusion, we're saying that dy dx in this case equals 1 over 2 square root of x. Okay, that's another way of writing your final answer. Okay, and so that's my entire purpose of example 2 right here. We walk through a few problems, and for you to understand, you know, you have your opportunity to work along and show your steps, and so that you can come to the final general derivative. And also you've learned the style so that you can use derivative symbols appropriately depending on how your function originally was written. All right, so give me a minute here to erase my board, and then we're heading into our next example. All right, and so now let's look at example 3. So just as I promised earlier to anyone viewing my video and to anyone studying calculus with me, there will be many occasions that I'm gonna get with any of you a problem about finding equation of tangent line. Because ultimately that's the very beginning, that's the very first motivation of getting, at least in my belief, in my philosophy of teaching calculus, getting the equation of the tangent line is the first motivation of, the original motivation of getting the derivative. And so at any point, no matter how far you've learned, at any point you're going to have a finding tangent equation of tangent line hitting back at you. Okay, so in example 3, so now you can kind of see where I'm going. All right, so I want to find, and I want you to work along, find the equation of the tangent line. Okay, and tangent line, but tangent to our function f of x equals square roots of, or how about actually let's not stay with square root because we've just had square root in a very previous example. So how about x squared minus 2x? Okay. Then now for tangent line, and we have to be specific at x equals 0. All right, so this is one complete finding the equation of the tangent line, tangent to a given function at a given value. So here our function that we have here is x squared minus 2x, and our given point of the tangent line there is x equals 0. And then so at the end, I mean right now you don't even see the graph, and you are not even required, the point is we're not even required to see the graph. So that's why, you know, I'm not going to be too worried about whether any of you have to have your graphing calculator with you. But the point now is that here, just whatever function you have, it could have a graph, it could have whatever crazy graph. I mean, maybe now you've been aware about the graph itself. The function itself is a quadratic function. So let's say it has a graph like this. Okay, but so whatever graph that is, x equals 0 is a point. So we want to find the equation of that line tangent to the graph here. That's the purpose right there. And this line that I'm drawing being a line, so we need to have mx plus b. That's the famous equation representing any line. And so being the tangent line, then usually I go with mt, which stands for the slope of the tangent line right here. This mt right here is the slope, but not any line. The slope of the tangent line, specifically for this tangent line we're doing right here. Okay? And so that's why big first step is always, and I also have mentioned that in some of our earlier lecture, but the first step now is to get the slope. But now slope, in this case, slope is the derivative of the function. So that means really first responsibility is to find out what's our derivative. And so our function is x squared. Okay? So now we're going to have to spend some time finding the derivative. So, and of course, anyone learning on this video lecture currently, I'm assuming that you're quite beginning. You're only a few weeks into learning your calculus. So there will be much nicer technique as well to get derivative. But for now, let's stay with what we've just learned, the limit formula, the limit definition. So for our derivative, we have to go with f of x plus h minus f of x over h, and take the limit as h goes to 0. And so now setting it up into our function. So but now I have to produce a pretty long looking fraction bar over here. Our function f of x is doing, this is what our function is doing to the input. It's going to square every input and minus 2 times the input. That's what it is. It's the rule for this function. And so f of x plus h. So now our input is being changed to x plus h. So now I'm going to have x plus h in parentheses minus 2 times x plus h. That's the rule of our function. The rule for our function. And then we need to subtract the actual function itself, the ordinary function itself. X squared minus 2x, and that's what I meant by the ordinary function, the function originally, over h. And ultimately, the problem needs to be a limit problem as we let h goes to 0. Okay? And so after a successful setting up point right here, that starting setup point, then we're going to proceed further. So now I'm going to take all that space in my other board for doing the work right there. But so, all right. And so now x plus h all squared from the previous steps can now be written as, and within just this lecture you have already seen x plus h squared quite a few times. So allow me not to show all the explanation anymore. But it's x plus h all squared can now be replaced by x squared plus 2xh plus h squared. Okay, and then minus, again, minus 2 in parentheses x plus h. So we can go ahead and distribute that minus 2, but watch out for a sign change right there. Okay, and so in that way, minus 2x minus 2h. That completes our f of x plus h right here. And now we are going to subtract. I am going to subtract. Again, recall from the previous step, minus x squared minus 2x. But now if we distribute that -1 or that negative sign to each term, expect the sign to change. So that means in my next step right here, it's going to be minus x squared plus 2x. That's how things are being done algebraically over h. And of course, I have to keep mentioning again. If any of you following along with the video and feeling lost a little bit or far lost, feel free to roll back or pause the video to allow yourself some time to digest the material and get caught up. Okay, and then you're gonna go ahead and resume. Okay, so suppose that you've been doing that. So now continuing with my work, this is a limit problem. Okay, and now at this point, I am going to start collecting either like terms or canceling out opposite terms. So x squared is opposite term with the other x squared that we can successfully cancel out. Okay, the minus 2x here is exactly opposite with the other minus 2x. I mean with the other 2x. So I am going to cancel those out as well. Okay, but everything we have remains now. There are no longer opposite terms. So we can write them, but at least they are a lot. The expression has become a lot simpler now. 2xh plus h squared minus 2h. Okay, over h, and this is limit as h goes to 0. Okay, and now at this point, once again, we recognize the same algebraic trick that we've been doing. See, recognize common factor, factor it out, and then cancel out with the h in the denominator. So I do recognize a common factor h throughout all three terms. So I am going to factor it out. My parentheses now contain 2x plus h minus 2. And I am dividing by h. Ultimately, the problem is a limit problem by letting h goes to 0. And so now, once again, algebraically, we can cancel out the common factor h here in numerator and the denominator. So in the next step, and once again, I have to keep reminding anyone, why do we have to go this far in terms of simplification? And over years of teaching, I keep having students asking me that question, Mr. Duong, how do we know how far is enough for simplification? Well, basically in my mental mind, at any step here, I have been doing that calculation whether or not I could be able to substitute in the 0 value for h, but none of these steps I can do that yet, because in the end we still have a 0 in the denominator up until the step. That's how. And so for calculus students, your mathematical level is mature enough. Please start doing that along the way and in every step. So at this point, when you get to this point right here, when you now at 2x plus h minus 2, then you can mentally tell that if you substitute in a 0 for h, which I don't recommend doing that, but limit laws do allow us to work things out just like substituting in. And so at this point, if you're substituting h equals 0 in here, we won't run into a trouble. That's where we know we don't need to simplify any further, and we're pretty much at dead end anyway. So that final expression would limit h go to 0. First term is independent with h, so that first term is simply just 2x, remains 2x after taking limits. This middle term is going to go to 0 as limits of x approaches 0. So that's plus 0. Last term is a constant term, so limit laws say it goes to the same limit, the same constant. And so our final expression here, after cleaning up the expression, it becomes 2x minus 2. Oh boy, we have done a lot of work right here. Okay, but really, what was our ultimate goal? I gotta constantly remind anyone. Our ultimate goal was to find the equation of the tangent line. Have we found that yet? Nope, not yet. We just about at the end, at the result where we found the general derivative. We will get there. But all that work we've been doing. So at this point now, we have found our f prime of x equals 2x minus 2. Okay, and so I will need a lot of board space. So if any of you viewing this video is taking notes along, make sure you pause the video and take enough notes right here, because shortly, once I erase all this, it's going to be gone forever. And okay, all right, so now into the problem, then this is what we've gotten up. The whole point of getting the derivative there is not that now. Okay, so now we can now say that the slope of our tangent line, mt, is equals to the derivative at x equals 0. So how do I know where that's? How do I know that's? To plug 0 in there, because the problem was asking us to find the equation of the tangent line, tangent to that function, to that curve at x equals 0. And so now the whole usefulness, and we started out since the beginning of this lecture until now, the whole usefulness is once we have found that derivative, that general derivative, then now we don't have to for other problems. We don't have to invent any further limit steps there. So now f prime here is going to be f prime at 0 is 2 times 0 minus 2. Okay, and we can find the slope of the tangent line easily by substituting x equals 0 into the derivative. Now minus 2. So now this is one big step that we have done. We found we got slope. See? Just like in some of our earlier video lecture I've done and highlighted the steps that anytime anyone would get into that kind of problem where we're finding the equation of the tangent line to a given function at a given point. First big step is to find the slope of the tangent line. So finding that slope of the tangent line might involve some crazy looking work by finding the derivative. So derivative have to come kind of before that. Sometimes derivative work could be long. Sometimes derivative work later on in the quarter can be a little shorter. Later on throughout our time learning can be shorter as you grow more mature in mathematics, in calculus. But at the end, highlighting it as a big major step, getting the slope down, nailing down the slope is one big step right there. Okay, and so our slope of the tangent line, to highlight, -2 at x, remind yourself at x equals 0. Okay, and so once we've found that slope of the tangent line, what a tremendous found already. So the next step now, our next step now is to get the tangent point. So I am also going to highlight the step. So we need to obtain the tangent point. And so those steps being highlighted, I am going to write them in red ink right here. So for any of you viewing this video, once again to have a general picture of how this kind of problem can be carried out anywhere. So tangent point here is simply just, well, we already had the x value of our tangent point. And imagine again, let me quickly swing to the other board, but your graph could be whatever. Tangent point is the idea is the point on the graph where the tangent line would go through it. Okay, so that's called tangent line. And so our problem was, in Word, it was already saying that find the equation of the tangent line at x equals 0. So we already had the x value of the tangent point given. So all we have to do now is to substitute that into the function, that x input into the function, and we got the tangent point. And so same idea, same understanding there. So now when x equals 0, right, my y value for the tangent point is the function value. See, so now I'm going to substitute x equals 0 into the actual function, not the derivative. Trust me, it sounds simple. It sounds very easy to understand this concept, but eventually I am going to have someone mistakenly substitute this value into the function, the f prime of x being 2x minus 2 that we have found previously. But this is not the function. It's a function, but not the original function that we're looking for, the tangent line. This is the derivative. Anyone hopefully getting me on that. So now again, substitute x equals 0 into your original function, f of 0. And so now f of 0 says f of 0 is right here. Because now since I put two functions together, it might be a little dangerous, but f of 0 now is you're going to substitute 0 in every x right here. So 0 r squared minus 2 times 0. And that gives me 0. Okay, so that means our tangent point, and let's make an overall conclusion. Our tangent point is 0 for x, comma 0 for y. That's our tangent point. All right, so now we are ready for completing our equation. So what do I mean by completing our equation of the tangent line? The tangent line, any line, is famously mx plus b, and in our case right here, mtx plus b, because I'm talking about slope of the tangent line. This equation is equation of the tangent line. We already found the slope. So we halfway completed that. So our line here would become, our slope was -2 that we found previously. So y equals minus 2x plus b. Okay? And so the next step now is to complete and find out what that b-intercept is. Well, b is called the y-intercept. I shouldn't say b-intercept. The b value, but it's the y-intercept. Y-intercept. Okay? And so at this point, I've introduced in earlier lecture a couple options right here. Option 1, a little more directly. Option 1, your equation currently found to be y equals minus 2x plus b. So we only have b left to find out. I am going to substitute the tangent point. The tangent point was right here, 0 for x, 0 for y. So I am now going to substitute the tangent point into our halfway completed equation. X for x, 0, y for y. So that means the y value is 0 equals minus 2 times x, but now x is substituted by 0 plus b. So that means we come down with b equals, easy enough to calculate, 0. So our final equation of the tangent line here, we have already found it, negative 2x plus 0, or for short, just minus 2x. This is our equation of the tangent line. Okay? Now, what if anyone not too comfortable with this direct method of finding the y-intercept? There's a different option. All I'm saying it's all about different option, and it's all the algebra. The more algebra you understand that you learn, the more options you have in terms of solving and handling your work. So now once again back to the ultimate goal. Pretend that we didn't go with option 1, okay? And we want to find what that b value is. Now, I introduced in some of the earlier video lecture, and I also had in some of my algebra course video as well. But there's a method that's called, we can start out by looking for the point slope equation. The point slope equation. Because this equation right here is slope intercept equation. We didn't get it there yet, but let's more easily. We can directly get on the point slope equation because we already had the tangent point. Let me remind you, we already had the tangent point, and that tangent point in the end stays on the tangent line as well. And so that's why to get the equation of the line, we can use start out with that easy form, the point slope form. So here's how the point slope form looks like. Y minus the y value of your point. Remind yourself, what I mean my point is the tangent point is being the point on the line as well. So y as a variable minus the y value of the point you already had, equal negative 2 as the slope, but times x minus the x value of your given point. This equation is called the point slope equation. And from the point slope equation, look at how nice that is. Y minus 0 is y equals, well, x minus 0 is x, so minus 2x. Now comparing the two answers, either you went with option 1 or option 2, you would arrive at the same equation of the tangent line. And in both ways, we're now at the slope intercept form of our equation of the tangent line that we're looking for. Okay, and that is our example 3 right there. And now let's get into example 4. And example 4, I can move on a little bit faster, and my aim for example 4 is to show how quick and how fast we can find, the different slope of tangent line. Equation of tangent lines. So example 4. Let's find the equation of the tangent line to, and our function given here is y equals x squared minus 1. Okay, but then I'm going to put a comma right there. I'm going to break it down to part A. How about at x equals 1. All right, and give me a minute to change my marker here. All right, so once again, remind yourself again that any line is in the form of slope-intercept form, y equals mx plus b. And our line here is being a tangent line, so I need that especially indicated it's mt, slope of the tangent line, mt x plus b. So our first big step is to find out what the slope of the tangent line is at x equals 1. But this time we use a different function. So this example, I want you to take that as close as possible, see that as close as possible to the earlier example. It's almost identical, except for I switch to a different function and I use a different tangent point. Okay, so after seeing some action in example 3, now you can see that once again, let's spend some time, and this part right here I can leave that for you. Let's find our dy dx, because in order to get your slope of the tangent line is the derivative, okay, at is the dy dx at x equals 1, okay. And for now I still have to bother spending some time writing all this down, but I will have all the explanation. Slope of the tangent line is the derivative, the general derivative at the given x value, x equals 1. So that means even before we can find the slope of the tangent line, we have to be able to find the derivative. So how about after doing quite a few different repetitive examples, I am going to show the setup, and I can leave that for viewers to complete and find out the final derivative on this function for me. So assuming that this is some f of x right here, even though we're using the equation notation, that's why it led me to using dy dx. So now f of x plus h minus f of x over h, taking limit as h go to 0. And so I can help one more step, and then I'm going to completely leave that for viewers to get the general derivative. So the next step would be x plus h all squared minus 1. That's how I substituted x plus h into my function, my current function f. But then once I've done that, then I am going to subtract my original function x squared minus 1, because the difference quotient say f of x plus h minus f of x. And that difference there, I am going to divide by h. It's a difference quotient. And we're dividing that, I mean we're taking the limits operation, letting h goes to 0. Okay, and so now at this point I am going to ask anyone viewing this video to go ahead and pause the video and work on your own right here, because I'm not going to show all the steps anymore. You are algebraically mature enough to carry out the step on your own. Okay, and then when you're back resuming the video, I am going to show that final derivative here. Okay, so assuming you already had your own work, so the dotted dot here is for you to show your own work right here. Your final answer at this point should be 2x for your general derivative, or in other words, we have found now dy dx equals 2x. So this is not our ultimate goal of the problem. This is just big part of the work right here, but we need the derivative to find the slope of the tangent line. So let's now move on to the slope of the tangent line. So I need a minute again to erase my board. All right, so now as far as and right now, because in my role in this video, I am teaching and leading your steps, so I still have to spend time writing down these, this step is for finding the tangent, slope of the tangent, and then the next step is the tangent point. But really, when you are doing this on your own paper and presenting it to any instructor, you don't have to write these. It's just as long as you be making it clear that this is your step to find the slope, and the next step is to get the tangent point. I'm giving a clear instruction, hopefully clear enough for anyone to grab that concept of how you find the equation of any tangent line, and as the entire picture step by step. So this step here, we're now about to obtain the slope of the tangent line. So the slope of the tangent line is mt, can be, so for the first time maybe in your calculus learning, the idea is the slope of the tangent line we're looking at is the dy dx. But in this way, it's hard to indicate how we substitute the value we found, x equals 1. Because we need to substitute this into our derivative. But our symbol right now is dy dx is a little too simple. And it doesn't have a place, not like a parentheses, for us to substitute in the x. And so here's what we commonly use right here. This vertical line is to indicate to substitute. So whatever expression we're looking at, dy dx, we're going to substitute x equals 1. So that's one symbol. It's indicating that to find the derivative, to find the slope of the tangent line, we need to go from where our found general derivative and substitute x equals 1 into that. So that means now our derivative is 2x, but x is substituted by 1. 2 times 1 equals 2. We had the slope. We have the slope now. So our slope here is going to be 2. But now at this point, let's look for the tangent point. Tangent point. Okay. X value of the tangent point was already given. But we need to substitute this point, this x value, into the original, the y value of the tangent point is the original function, which is in this case 1 squared minus 1. That was, allow me to remind everyone, the original function that we're substituting x equals 1 into. And so at this point, our y value for the tangent point is 0. Or in other words, our tangent point is 1, 0. That's the tangent point. Okay? And it's just me that I'm personally more into going with that option to find the slope-intercept form immediately. Because our next step now is to get the equation, to complete the equation. So our equation is halfway done. Y, at this point, y equals 2x plus b. I am going to go with my option 1, but if you're more comfortable with option 2, go for it. It's all about, we're going to have to eventually arrive at this point. So 1 substituted for x, 0 substituted for y. So 0 equals 2 times 1 plus b. Okay, and so my b value is directly found to be, quick calculation, we're going to subtract 2 from both sides here, and so b equals -2. And so now our final equation. So this is going to be just final equation is here. Okay, so we get that final equation. So now our final equation. In some of the earlier video lecture, I might have broken that into a fourth step where, before this step 3 right here, it was, finding the y-intercept as one separate step, but which is that work right here. And then eventually putting it all together as one equation is a fourth step. But here, since you are a little more mature, finding the y-intercept and putting it all together as an equation, I consider now as one step. But your final equation now is y equal 2x minus 2. That's your equation of the tangent line, and that's how it works, and that's how the steps are. Okay, and so we are not moving away from example 4 yet, but let me now introduce. So let's look at part B. Okay, and there's a reason why you probably feel a little shocked that I don't erase any of this here. But part B of the example. Same function. So here's how it reads. Find the equation of the tangent line to y equals x squared x squared minus 1. But now I'm just simply switch to a different value. X equals -1. Okay? And here's the reason why. So here's the reason why that I did not erase any of this work. Because in the end, we are still remaining on this exact same function. And so that's why we're expecting the same general derivative. So I don't want anyone viewing this video will feel like that you don't need to reinvent the entire wheel. All that work is still here. You can reuse it. It's completely legal. Okay? And so now, as long as we stay with the same function, then all that work here we can remain the same. Will remain the same. Our dy dx is the same, 2x. So the only thing difference now, allow me to navigate to the other board and make sure anyone is taking note, clearly or carefully about our given point x equals -1. That's the only thing that we switched. Earlier we were finding the tangent line at x equals 1 in part A, and now in part B with same function, but we switched to a different place right here. X equals -1, and we're trying to find the tangent line right here. All right, so enough beating around the bush. Now let's get to it. All right, so, and now I can just leave all the structure here. I can leave all that structure here, step 1, step 2, and step 3 all here, so that we can just simply fill in the work. But like I said, because I'm the instructor showing the work in this video, and so I have to break it down into steps and steps and steps like this and label my steps. But really, my students, anyone studying with me, I don't really have to require you. You're not really required to label these steps. Just clearly show these steps. That's all it needs, and I believe any instructor would look for just the same thing about me. So, slope mt. Okay, so the slope for our equation is once again the derivative that we have already found, but this time we're going to evaluate that at x equals -1. We switch to a different place to find our tangent line. And so, but that symbol just means we're substituting x equals -1 into our currently found dy dx. And that's the reason why being able to find the general derivative is such a beautiful work. It's a one-time investment. Once you found it, you can find 10 different tangent lines as long as we stay in the same function. 10 different tangent lines, but in pretty much no time. I have to spend a lot of time explaining the steps, and that's the reason why it takes a little bit of time. But once you are fluent with that, that's my aim for any of this, then it's going to be a lot faster than how I carry the steps up here. Okay, and so this is going to be 2 times -1. Okay, and our slope here is now -2. And then, so once we've had the slope, then the tangent point in this case, x is given to be -1. So the y value of our tangent point, simply just substitute that into the function. X squared, but now x is -1, so -1 squared minus 1. Remind yourself, we're substituting the given x value into the original function, not the derivative. And that here gives me 0 again. So the tangent point is -1, comma, 0. That's the tangent point. And so now to find our final equation, then with our equation of tangent line halfway found, halfway completed, minus 2x plus b. We only need to find that remaining y-intercept, and we're done. So in that way, with the tangent point, and again, it's just me personally, I like to go with the option 1, meaning I'm going to directly substitute this into my halfway found tangent line equation, and then solve for b, rather than going with that point slope, even though it's pretty much about the same amount of time and the same amount of effort. So here, 0 for y equals -2 times -1 for x plus b. So now my final value for b can be found to be b equals -2. Okay, and once again, if you need a little time to get caught up, pause the video and do the calculation carefully to make sure you agree with mine, like that. But now at this point, so now we are ready for our ultimate goal. Our equation of the tangent line at x equals -1 is y equals -2 is the slope, -2 x minus 2, and this is the equation of our tangent line. Same function for the same function, but switch to a different x value. So we're expecting a different equation of the tangent line with them. And so now this is the graph of this red graph right here is the graph of our f of x equals x squared minus 1 function. And so at the end of example 4, now let me quickly show how to show a graphical explanation of our different tangent lines. So since we have the same function x squared minus 1 throughout all part A and part B, and so derivative was found to be 2x. And so once we found the derivative, then when x equals to 1, as in part A right here. So now let me put on the tangent line right here. So the tangent line in green. So if anyone viewing this video is experienced enough now to tell that this line, the tangent line of our x squared minus 1 function, this tangent line is having a slope positive 2 because we did our calculation. And the equation here, the line itself is going through y-intercept -2. And so in that way, that's how it's consistent with our result that we calculated earlier, that our tangent line equation was y equals positive 2x minus 2. Okay, and then in part B, look at how I switched that to part B right here. Part B was we were looking for the tangent line, the equation of the tangent line at x equals -1. So when x equals -1 right here, then we repeat all that work finding the slope, and our slope was -2 according to our calculation. And so the graph right here is also agree with that. It drops by 2 squares down and over by 1 square to the right. And so we're looking at the slope being -2. And also this line in green graphically is going through the y-axis at -2. And that's the reason why altogether it's agreeing with what our results show, that our final equation of the tangent line here at x equals -1 was -2 minus 2.